Well, good morning, everyone. Today we are going to do Chapter 8. I'm talking about acids and bases. First of all, we're going to talk about hydrogen bonding, the concept of autophotolysis, then ionization of molecular compounds, strong acids, strong bases, conjugate acid-base pairs, neutrality, and the pH scale. Now, all of this is pretty much descriptive except for the very last one here, pH calculations. I did ask that everyone bring your calculator because I really want you to practice doing these calculations with us so that you know what to do on the exam and tutorials, stuff like that. Just as a warm-up, if you could pull out your little calculators, type in the number 3000. Then you need to figure out how you get to the log function. Type in log. Click on the log button. That's mine right there. You should get 3.477. Now, the other function you need is 10 to the x. On my calculator, I have to hit the green button, and then this thing here. When I do, I should get 3000 one more time. Now, depending upon your calculator, rounding errors may be slight, but you should be very close. Any questions? All right, well, in Chapter 7, we decided that water was going to be a polar molecule. The electronegativities of hydrogen and oxygen are significantly different. We have two dipoles here on these covalent bonds, and this gives rise to a molecular dipole in the molecule. We confirm that by looking at the electrostatic potential map. For water, we have a big blue bottom. The hydrogens are here and here. And of course, this is where the electrons are, and that's all oxygen. We said the fact that water was polar as a molecule allowed it to interact with ions. It interacted both with cations and anions, dispersed the charge from these point charges, and thereby stabilized these ions in solution. This is the way that we can dissolve things. Again, you have to take the charge and spread it out. Now, I contend that since water is a polar molecule, and water is obviously capable of interacting with charged particles, that water should also be able to interact with itself. So here we have water, there's our two hydrogens, there's the oxygen. We have two positive ends, and we have a negative up top. Actually, two negatives because there are two pairs of electrons. But if one water molecule were to encounter a second, it could stabilize this charge dipole by bringing the water here, put the negative end next to a positive oxygen. When we do this, we form a bond. Now, this is not a covalent bond. It does have energy. It's about 5% the energy of a standard covalent bond. So that's weak. But the way water is designed, we have another hydrogen over here. We can very easily bring another water in and form a second hydrogen bond. We also have a negative region up top We could bring a water in, turn it, and form a third and eventually a fourth hydrogen bond to this one central water molecule. What this does, number one, is to spread out the charge among the complex, and that stabilizes it. And it also provides great stability to water as a molecule, as a structure. This is what one water molecule bonded to four others by hydrogen bonds kind of looks like. This over here is a result of another calculation. What we did here was to ask the computer to take a lump of water, allow it to form hydrogen bonds, and then do a space-filling model that shows where the electrons are. And I want you just to appreciate this lump of water. You can see the hydrogen bonds here, and there's one here. Some of these things, the neighbors has entirely swallowed the adjacent hydrogen. One hydrogen bond doesn't make very much difference, but in water, we have an extensive network of hydrogen bonds that can form. Now this is very, very dynamic. Every 10 to the 8th seconds, this entire thing reorganizes. It kind of looks something like this. Once again, this is the result of a calculation. The little purple lines that keep popping in and out are hydrogen bonds. This is slowed down by a factor of 1 billion so that we can see what's going on. If you look at that, you can see again, hydrogen bonds make and they break, water molecules move around. Water is a very low molecular weight substance, and yet it has a high boiling point. The reason it does is because water molecules are literally hanging on to each other by this hydrogen bond network. Now, if you look at this very closely, most of these are waters, but every now and then you'll see a water that only has one hydrogen, and you'll see the same number that have 3 hydrogens. This is the polyatomic ion hydroxide anion. This is hydronium, H3O. This is negative, this is plus. We'll see that this arises by the process of autophotolysis. So, let's go back to my models. Here we have 2 waters, and they're happily hydrogen bonding to each other. If one of these gets just a little kick, a little bit of extra energy, somebody bumps into it or whatever, the hydrogen here that's involved in this hydrogen bond can quite literally transfer from this water molecule to this one. Something like this. We have now formed our hydronium ion, H3O+, and our hydroxide anion, OH-. As we saw in the movie, these things are dynamic, so this can hand it back just as fast as it took it in the first place, and this process will go back and forth and over and over and over and over, roughly 10 to the 8th times per second. Let's let it do it one more time. The conclusion here is that if we have pure water, absolutely pure 100% water, because of this autophotolysis that goes on constantly, there's always going to be hydronium and hydroxide ions in our solution. Now the concentrations are small. In water at 25 degrees, the concentration of hydronium and hydroxide are equal, and they're both 1 times 10 to the minus 7 moles per liter. But they're there. This is an important concept. If we have absolutely pure water, the concentration of hydronium and hydroxide are going to be 1 times 10 to the minus 7 moles per liter each. Any question on the concept? It all arises due to hydrogen bonding. If you recall back in chapter 7, we were talking about electrolytes and non-electrolytes and don't go in the tub with your hair dryer, stuff like that, important stuff. We said that there were ions in tap water and therefore you could be electrocuted. Well, when we look at the conductivity of pure water, it wasn't zero, was it? It had a distinct number. It was much smaller than an electrolyte, but still it had a small conductivity. This is the hydronium and hydroxide that are always there. So bottom line with this one, even if you have a tub filled with distilled deionized water, you still can't take your hair dryer in there because there's still ions, and yes, it's not good for you. Any questions? All right. Well, these ions that we have formed are charged particles, again, in solution. This is hydronium, this is hydroxide. They're both very highly charged. Just like ions in solution in water, the only reason that these guys can form is that water can disperse the charge. Let's just look at that. Let's deal with the hydronium ion, H3O+. Here it is. We're doing a top view here. Here's the green oxygen. If we flip this guy on its side, you can see the huge blue bottom, and again, a green cap for the oxygen's electrons. When we had this same sort of situation with ions, we did a calculation where we took our ion and surrounded it by 3 waters. We can do this again. If we take our hydronium ion here, and we simply place 3 waters around, we're letting the negative end of the dipole interact with each of the hydrogens, which are the positive ends. Now, once again, this is our big blue ball in the middle. If we do our calculation, the electrostatic potential map shows the oxygen in the middle here to not only not be greenish blue anymore, but now it's pretty much yellow. So just like with ions, even 3 waters are capable of dispersing this charge. But if we remember what we saw just a little bit ago, water doesn't live in groups of 3s, does it? Water exists as a large extended family. Let's do this again with hydronium in the middle, and I've got 9 waters here all around it. They're all busily hydrogen bonding and interacting with the cation. Here's what our cation looks like. Again, very, very positive. We asked the computer to take this entire cluster of water and do an electrostatic potential map to show charge distribution. When we do that, we get this thing. Now, this in the middle, this guy right here, is our hydronium. Big blue ball, big cap. Just these 9 waters around it, we now have restored the dipole in this. It's lovely red, and we have dispersed this charge over this entire complex. Kind of amazing the way water can do that. All right, water is amazing. Yes, it is. If water is capable of interacting with itself, that leads to ionization, it can also interact not only with ions, but with other polar covalent bonds. So let's just look at our friend here, hydrogen fluoride. Hydrogen fluoride is what we looked at as our very first example of a polar covalent bond. Nice big dipole here, positive end, negative end. If we put hydrogen fluoride into water, the water will interact with both ends actually, but let's just do this guy. Here comes our water, and again, it's going to form a hydrogen bond. Now, just like we had with water itself, if either of these gets bumped or just gets a tiny bit more energy, or just gets tired of being left where they are, this can move from here over to here and form a hydronium and the fluoride anion. Once again, just water by itself has been able to take this polar covalent bond and break it. The equation describing this, hydrogen fluoride plus water, is hydronium ion plus fluoride anion. Now, sorry. So, hydronium plus fluoride. Just like we had with water, we said that once we transfer the proton from HF to water to make a pair of ions, we can also transfer the hydrogen back to give our starting materials. Both of these reactions go on simultaneously. They go on at the rate of roughly 10 to the 8th times per second. When we have a reaction like this that goes this way and that way and this way and that way at the same time, in chemistry we call that an equilibrium. And for an equilibrium we use a special set of arrows. It's not a double-headed arrow, that's different. These are two arrows this way and that way. When you see that, that tells you that this reaction rapidly goes this way and that way constantly. Okay, so this is our equilibrium dissociation of HF. The equilibrium dissociation of HF yields us hydronium and fluoride anion. Whenever you have a polar covalent bond that undergoes ionization in water to give hydronium, we call that compound an acid. An acid means it hits water and gives hydronium. And it's an equilibrium, going back and forth very, very rapidly. There are two types of acids that we deal with: weak acids and strong acids. They differ in their equilibrium. Let's just pretend that this reaction, the forward reaction here, is going very, 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 very fast. And the reverse reaction is going very slow. That means if you take a snapshot, it's going this way really fast, this way really slow. So at the equilibrium position, you'll have more of this than you will this. That's a strong acid. Weak acid, just the opposite. Put it in water, it does ionize, but not much. So we get a little bit of this, and almost all of it is this. Weak and strong. Let's look at an example here with a strong acid. This is hydrochloric acid. It's a strong acid, just like nitric, sulfuric, phosphoric. All of those are strong acids. They will ionize essentially completely in water. This is a little clip that's almost useful. We have HCl and water, hydronium, and chloride. We'll start off with our HCl. What we're going to do is place this into water and watch what happens. Again, this reaction is going very, very fast. So instantly, it seems, all of these ionize. Essentially 100% into ions. Now the back reaction still goes, but the ratio of this to this is roughly 1 billion to 1. So there's always got to be 1, but it's 1 billion to 1 ratio. A weak acid, just the opposite. Once again, this is acetic acid. Acetic acid is a weak acid, but it does ionize to give hydronium and acetate anion. When this goes into solution, it will every now and then ionize. So this reaction is very slow. This one is very fast. That's a weak acid. Any questions? Well, in 110, we are going to deal only with strong acids. Weak acids are general chemistry stuff, and when you cover equilibrium in general chemistry, this is the kind of thing that will really be very important to you. Weak acids. But here we're going to deal only with strong. Examples of strong, we've done hydrochloric acid, hydronium and chloride. Nitric acid is basically just nitrate with a hydrogen on one of the oxygens. Perchloric acid, we take perchlorate, and again we can put 1, it's a -1, so we can put 1 hydrogen on. This is perchloric acid. These all liberate 1 mole of hydronium per mole of acid. We tend to call these monoprotic acids, 1 proton. Now, why is it called a monoprotic? Why is we dealing with a proton? Do you remember the little videos that we showed? When we transfer the hydrogen, it transfers as H+. That's a proton. With no electrons, it just slides across the hydrogen bond. So it is transferred as a proton. Again, it's called proton transfer for that reason. In lab, we also deal with 1 diprotic acid. Everybody's favorite. It's sulfuric. Sulfate is a -2 ion, so we can put 2 hydrogens on. We can lose these one at a time. Sulfuric acid will ionize the first time to give hydrogen sulfate. Hydrogen sulfate can undergo a second ionization to give sulfate, hence this is called a diprotic acid. In lab, we also deal with 1 triprotic acid, and that's phosphoric. Again, phosphate is a -3 ion, so we get 3 hydrogens on it. And just like sulfuric acid, we can pick these off one at a time. Any questions? All right, there are ways to describe what's going on in acid-base reactions. The proton donor in an acid-base reaction is called the Bronsted acid. We'll see that in a second. And it's the thing that actually donates the proton. The Bronsted base is the thing that actually accepts the proton. There's also Lewis acid-base theory. That's different. Here we'll talk about Bronsted acid-base theory pretty much exclusively, and especially within the context of conjugate acids and bases. Conjugate acid-base pairs. In this equation, nitric acid is donating a proton to water. That makes it Bronsted acid, Bronsted base. After you have donated the proton, what's left? Nitrate. We describe this as the conjugate acid and this as the conjugate base. Nitric acid is the acidic component. It's the acid. After it donates its proton, what's left is nitrate. That's the conjugate base. In general, the conjugate base has one less hydrogen, one less proton, and one more negative charge. Now once again, this is the Bronsted acid. It is the thing that is the proton donor. This is the Bronsted base, which is the proton acceptor. And after we have donated its proton, we're left with the conjugate base. So that's the important nomenclature. Any questions? Well, let's do a quick set of problems here. For these 4 reactions, I would like you to identify conjugate acid-base pairs. All right. Remember, conjugate acid donates the proton. When it does, it forms its conjugate base. So they're the same thing, except minus the proton. That would make HCl our proton donor. After we remove the hydrogen, we're left with chloride. This is our acid, and this is its conjugate base. Okay. This is the first ionization of sulfuric acid. This is the acidic form. It's going to lose its proton. When it does, it forms hydrogen sulfate cation. This is the acid, and this is its conjugate base. The second ionization of sulfuric acid. Again, this is going to be our acidic component. When we lose the hydrogen, we're left with sulfate. Conjugate acid, conjugate base. Now, interestingly, liquid ammonia, if you think about it, is going to have polar covalent bonds just like water. And it will hydrogen bond just almost like water. It's not quite as good, but it can work. There's actually reason to think that liquid ammonia, like occurs in oceans on faraway planets, could support life because it is polar enough, it hydrogen bonds enough, it can dissolve ionic substances, just not as well as water. All right, if we take nitric acid, this is our Bronsted acid. This is going to accept our proton, so that makes it the Bronsted base. After we donate our proton, what do we have? Nitrate. Conjugate acid, base, pair. Now once on an exam, just to be nice, I put this equation on, and I asked the class to identify the acid and conjugate base pair for the reverse reaction. So starting here, going this way. Think about it for a second. Over here, we have an acid form, something that's going to donate a proton. After it donates its proton, what's left is its conjugate base. Now actually here, the only thing with a proton is ammonium ion. So if ammonium ion is the acid form and it loses its proton, what do we get? Ammonia. So forward reaction, that's the acid base, acid conjugate base pair. Reverse reaction, acid conjugate base pair. Any questions? Well, there's a tutorial about this. In this guide, you have blanks and you simply have to enter the species. Now, of course, you can't use super subs, you just type in whatever you can. And you have to do this in the order that it's given. So fluoride is going to have to be here, water, whatever is going to have to be here. So we look at this and we say, gee, something donated a proton and formed fluoride and ion. So this is the conjugate base. If you go and put a proton on fluoride and ion, you would get HF. This is the conjugate acid-base pair. Here we have hydronium. Hydronium is the acid on this side of the equation. It was the Bronsted base on this side. So it accepted a proton. What accepts a proton and makes hydronium? Well, it's water. That again. This is chlorate. This is hydronium. Our acid form is going to be here, H3O+. When we transfer the proton to the Bronsted base, what do we get? Chloric acid. All right, after we transfer, what is the conjugate base here? It's hydronium minus a proton or water. Just look at this one and see if you can fill it in. Blackboard looks the same thing, same way. Again, you can't use super and subs, and just type it in, any way you can. Here we have two potential acids, don't we? Hydrogen sulfide would be an acid donated to this as a Bronsted base, but there's no place to put it. Okay, we've kind of like used up all the spots on our oxygen. This is going to be our acid. This is going to be the Bronsted base. So, starting here, if this accepts a proton, what do you get? H2SO3, sulfurous acid. This was our Bronsted acid. After it loses its proton, what do we get? Water. Any questions? All right, on your exam, you will have questions regarding conjugate acid-base pairs. And again, this is a Blackboard tutorial as well. Please make sure you understand the concept. All right, I said we had strong acids, weak acids. If we have strong acids, it's only fair that we also have strong bases. Now, basically, a strong base is going to be an ion compound, dissolves in water, forms a cation and hydroxide cation. Now, if we take a strong base, so we're talking hydroxide anion, and we mix it with a strong acid. Strong acid has hydronium. Hydroxide and hydronium will immediately react and form water. This is your classic acid-base reaction. Hydronium plus hydroxide gives water. Now this is an equilibrium, isn't it? So it goes back and forth. But we've seen this equilibrium before. If you just simply take and reverse this equation, like flip it over, this is the autophotolysis equation, isn't it? And we know that if we have water, we get hydronium hydroxide, but we get 10 to the minus 7 moles of these guys. So it's mostly water. Over here, we take them, we react them, the equilibrium is shifted this way by 10 to the 7th fold. This is an acid-base neutralization reaction because we're forming neutral water. Let's look at it in a cartoon. Here we have hydronium and chloride anion. That's HCl in water. Okay? Over here we have sodium hydroxide, sodium and OH minus. If we take these two and we mix them, we have sodium and chloride ions in our solution. We have hydronium and hydroxide. But again, we know as soon as these guys hit solution together, we're going to transfer the proton from here to here and wind up with water. When you do a neutralization reaction, what do you wind up with? Sodium and chloride ions in water. This is also described as being a salt dissolved in neutral water. There's a salt in water. Now remember, our water still has 10 to the minus 7 molar hydroxide and hydronium. You can never get away from that. Let's look at a couple conjugate acid-base exam questions. In this problem, we have pairs here. We're looking for the acid followed by its conjugate base. Now we remember, the acid loses a proton to form its conjugate base. So everything has to be there except the proton. If we lost H plus here, what would we have? Nothing. Certainly wouldn't have HCl, that's wrong. If this was our acid and it lost a proton, it would form NH2 minus, wouldn't it? Not NH4. If this loses a proton, we would form phosphate, not hydrogen phosphate. If hydrogen carbonate loses its hydrogen, what does it form? Carbonate. By George, that's an acid-base pair. Here, we are not losing a proton, we are gaining one. So D is our correct answer. Any questions? Here's another version of essentially the same problem. Hydrogen carbonate with water gives carbonate and hydronium. And that's followed by way too many words. So, hydrogen carbonate is an acid. That's true, it is. Water is its conjugate base? No. Hydrogen carbonate loses the hydrogen that gives carbonate. That's wrong. Hydrogen carbonate's an acid. Yes, it still is. Carbonate is its conjugate base. We lose our hydrogen, we get carbonate. That one is correct. Well, H3O plus is an acid. Yes, it is. But if we lose a hydrogen, we don't get carbonate, we get water. Water would be an acid, but carbonate is not its conjugate. And finally, hydronium is an acid. Again, if we lose this, we get water, not carbonate. Any questions on that one? Simple one here. The conjugate acid of hydrogen sulfate is what? Conjugate base is formed when the acid loses a proton. The base gains a proton to give its conjugate acid. So we simply take hydrogen sulfate and sulfuric acid is our conjugate. Any questions? All right. Let's return and talk about the concept of neutrality. So back to our bathtub. We know that there's always a very small extent of hydronium and hydroxide in pure water. At 25 degrees, both of these are 1 times 10 to the minus 7 molar. That's a small number. So again, it's mostly water, tiny bit of this stuff. Now, when you're dealing with acids and bases in solution, typically these equilibrium constants are going to be very, very small. That's a way of saying the concentrations are very small. In order to make this, quote, easier to work with, a Danish chemist named Sorensen, looks like a name, doesn't he? Danish chemist suggested that pH could be a convenient way to express acidity. he defined the term pH as the negative logarithm of the hydrogen ion concentration. Minus log H3O plus is pH. Now, when you see it written, it can either be H3O plus or quite often just simply H plus. Just a shortcut. Okay. The negative log of the hydrogen ion concentration. Once again, P is simply an abbreviation here for negative log. That's what that means. Base 10 log is the number to which the number 10 has to be raised, the power, the exponent, to produce that number. At the start of class, we took 3,000 and took its log. It was 3.4, right? Then if you took 3.4 and raised 10 with 3.4 power, you got your 3,000 back. So the logarithm is simply an exponent. If we multiply 10 by 10, we get 10 squared, right? The log of 100 is 2. It's simply the exponent. 10 times 10 times 10, 10 to the third. The log is 3. If you have 316 and you enter it in your computer or calculator, you'll see this is 10 to the 2.5. Why don't you try this right now? Take your calculator, type in 316, hit log. You should get 2.5. Take your calculator, find 10 to the x, type in 2.5, hit 10 to the x, you should get 316. It's simply the exponent of 10. Any questions? All right. One other question. What are with these little square brackets? That's one convention in chemistry. Whenever you put a substance inside square brackets, it refers to the molar concentration. So this is the negative log of the molar concentration of hydronium, SPE. Okay, so what's the consequence of this? We know that neutral water, hydronium, is 10 to the minus 7 molar, right? The log of 10 to the minus 7 is what? What's minus 7? It's just the exponent. The negative log. So multiply this by minus 1. What do you get? 7. Hence, the pH of absolutely pure neutral water is 7.0. That's where pH 7 comes from. Because hydronium is 10 to the minus 7. Take the log, change the sign, the pH is 7. If hydronium is greater than 10 to the minus 7, so you have more protons, it's acidic. If it's less than 10 to the minus 7, you have fewer protons. Therefore, it's basic. This is something worth remembering and writing on the back of your hand. If the pH is less than 7, your solution is acidic. If the pH is greater than 7, the solution is basic. Any questions? 7, exactly 7, is neutral. All right. Again, if we can have a pH scale, it's only fair that we have a pOH scale. It's the same thing. Remember, P stands for negative log. This is the negative log of hydroxide concentration. Now, in neutral water, hydronium and hydroxide are both 10 to the minus 7 molar. If we multiply these two concentrations together, we get 10 to the minus 14, don't we? Now, let's take each of these and take its negative log. This is hydronium. That's going to be H3O+. The other one was hydroxide. That's also 10 to the minus 7 molar. So this times that is this. If we take the log here, under all conditions, this is a true statement. Now, let's go one step further. Convert this to pH. Convert that to pOH. This is simply the exponent. The negative log pH plus pOH is 14. Those two are extremely important things to remember under all conditions at room temperature. Hydronium concentration times hydroxide is always 10 to the minus 14. Always. And pH added to pOH will always be 14. Let's just do the first one here. If I give you either hydronium or hydroxide concentration, using this, you can instantly calculate the other. So, if I tell you that hydroxide was 5 times 10 to the minus 8, that's this. In order to get hydronium, you would take 5 times 10 to the minus 8. You would move it over here. Your math is 10 to the minus 14 divided by 10 to the minus 8. This guy, this is hydronium ion concentration. Take and multiply them together just to prove it to yourself. You're back to 10 to the minus 14. Again, this is true under all conditions. Regardless of these two concentrations, they'll always be 10 to the minus 14. pH plus pOH, likewise, will always be 14. Very useful things. All right, let's talk a little bit in general about pH. This is our pH scale. 7 is absolutely pure neutral water. Bad coffee is down here around 5. Really bad wine is around 3. Stomach acid, a little bit above 1, 1.2, 1.3. It's amazing the stomach just doesn't resolve itself. 1 molar HCl would have a pH of 0. On the basic side, blood, sweat, and tears, just over 7. Bleach ammonia solution in the 11 to 12 range. 1 molar sodium hydroxide is up here at 14. How do we measure pH? Well, the most accurate way to measure it is using this thing It's called a pH meter. What it is basically is a voltmeter, millivolt meter, very, very sensitive. You put an electrode into your solution. The electrode looks something like this. It has a couple chambers, has a very, very, very thin glass membrane. When I say very thin, it is thinner than a human hair. Which means that if you walk up to this thing and do like that, it's broken. In lab at UIC, when I had the big research group, we would go through these things. Well, let's just pretend you start a new student, okay? During the first week, I can guarantee they will break half a dozen of these. It gets better over time. But in the day, we paid $2,000 a piece for these. So I would sit in my office and just grimace every time somebody new started. But this is a protected thing. It's not nearly as accurate. It's only about a couple $100, but still they won't let you use that. Instead, this is what you would most likely use in lab. It's called pH paper. Now, pH paper is literally just a strip of paper with indicators mixed together at a special certain concentration each. Remember, the indicator is a chemical that undergoes a color change according to pH. In lab, we saw one, phenolphthalein. Phenolphthalein, here's a model, here's the organic structure. In an acidic solution, it was colorless. And when you had a basic solution, it turned this bright pink. Okay. Well, to make pH paper, somebody looked at the entire list of available indicators. And you see some of these are fairly complicated in their color changes. And came up with a perfect mixture. So you start off with pH 7 is green. If you dipped it in water, it would stay green. If you dipped it in acid, it would turn bright red. And if you dipped it in an alkaline solution, it would turn bluish black, purple. To come up with this really was a major achievement. It really was. It's cheap, it's useful. You could just dip your little piece of paper in and know where you are. But as clever as whoever that chemist was, the red cabbage beat us to it. Turns out if you take red cabbage juice and put it in acidic solution, it's bright red. If you raise the pH a little bit, so it's neutral, it's purple. You go up a little more, it turns blue. And finally, if you make it alkaline or basic, it's green. Now, most chemists like to cook. Okay, cooking is like chemistry. And knowing this is very useful. If you took red cabbage and chopped it up and sauteed it just in the pan, it turns out this kind of old reddish purple stuff. Tastes great, right? But if you want to make this really pop, you take your red cabbage juice, you add a little bit of vinegar, makes it acidic, and your red cabbage looks like that. Halloween is tomorrow. If you wanted to serve red cabbage and have it meet your expectations for Halloween, add a little bit of baking soda to it, make it alkaline, and you get that. Ugly. Now they all taste like red cabbage, but a totally different impression on the serving dish. Any questions? Okay, titrations. I keep saying general chemistry, yeah. In general chemistry labs, you live and die by titrations. You'll do lots and lots and lots of them. Hope you all get there. This is called a burette. It is a thin tube, hollow, and it's marked off in milliliters. As a stopcock here, you can open this, and the stuff will dribble into a vessel. To do a titration, you start off with a known solution. Here, let's pretend we have a solution of base down here. I'm sorry. And we have a solution of acid down here. And we're adding base to our burette. Step 1, you mark down the level exactly as you can read it where your titration starts. Down here in the acid beaker, you put a drop of indicator. Then you very, very carefully open this. When you hit neutrality, your indicator changes, you shut this, and you measure your level here. So here we're pretending we added roughly 15 mils to get our color change. Well, we know the volume that we added. We know the concentration of this stuff, because this was a known solution. Concentration times volume is moles, so you know exactly how many moles you added, which must equal the number of moles of acid that were down here. Nice, simple titration. Allows you to take an unknown and a known solution and figure out the concentration of the other. Now, we kind of did a titration in lab. Kind of. This was in lab 6, I believe. We took our 26-well plate, this one was clean, and we added nitric acid to one well, exactly 10 drops. Sulfuric acid to the next well, 10 drops, and phosphoric acid to the third. This is a monoprotic acid, a diprotic acid, and a tri. We put a drop of indicator into each one, then took our strong base and added it dropwise. For nitric acid, we slowly added our base. It started off colorless. After a couple drops or so, it turned color. Okay, that was the monoprotic acid. For the diprotic acid, did the same thing. First 2 drops, take the first hydrogen off. The next 2 drops, take the second, and now we're basic. For our triprotic acid, did it 1 for the first hydrogen, another one for the second, and the third. Finally, to get our color change. Now, it didn't always work that way, did it? Some people got kind of skewed numbers, but this is the way it was supposed to work. Any questions? Well, we understand now what pH is. We can write a definition and all of that stuff. How do we do pH calculations? If I tell you I have a solution, I stick my meter in, the pH is 7.23. What is my hydronium ion concentration? Well, there are a couple equations that we need to know that you probably should write on your little handy card for the exam. The first one, pH is going to be the negative log of hydronium. Now here we know pH, and we're looking for hydronium. First thing we want to do is get rid of this negative sign. I'm a positive person. I don't want the negative sign, so I'm going to multiply both sides of the equation by -1. We have minus pH log hydronium. Okay. Now, I'm going to do something called taking an anti-log. The anti-log. Remember, a logarithm is just an exponent, isn't it? An exponent of 10. So the anti-log of minus pH, that's just a number, is going to be 10 to the minus pH. Now, the anti-log of something that's already a log, well, the log disappears. 10 to the minus pH equals hydronium. We substitute our numbers in and then pull out our handy calculator. At least you guys do. When I was a child taking chemistry, we didn't have calculators. In fact, in every textbook, the last half inch were these things called log tables. And you would sit there and flip through this huge stack of numbers to match up a logarithm and a number. Fortunately, today all you have to do is click. So how would we solve this? We're going to use 10 to the x. This is 10 to the minus 7.23. So we're going to type in minus 7.23. You could play along with yours if you want. We hit inverse log, which gives me 10 to the x, and we get this number. This is the hydronium ion concentration. 10 to the minus 7.23, 5.89 times 10 to the minus 8 moles per liter. The important equation here to be on your card, 10 to the minus pH is hydronium. All right, let's do a problem or two. If I tell you the pH is 4, what is hydronium? Well, 10 to the minus pH. You simply take 10 to the minus pH, substitute, is 10 to the minus 4. What is hydronium? 1 times 10 to the minus 4 molar. If our pH was 12, what would it be? We're going to take our pH value. It's going to be 10 to the minus pH. That's 10 to the minus 12. And that's our hydronium. (5.5). Type in minus 5.5. hit 10 to the x, 10 to the minus 5.5, 3.2 times 10 to the minus 6. 1.32, 10 to the minus 1.32. This guy, hit 10 to the x on your computer or calculator, and we're at 5 times 10 squared. This number, I put this in because back in the research lab again, with our $2,000 electrodes and our students breaking them like mad, our pH meter was actually capable of measuring that closely. It was also very expensive. Type in 10 to the minus 7.02 whatever. It equals, and we're 9.4 times 10 to the minus 8 molar. Now, which of these solutions are going to be acidic? Remember, the more hydronium you have, the stronger the acid. The cutoff for neutrality is 10 to the minus 7. So this is below 7, it's acidic. Above 7, it's not. Below, it is, and it's not. These are the guys that are acidic, and these two are basic. Any questions? All right. What if we know hydronium and we want the pH? Okay, we can do that. This is our hydronium from the problem. We know that pH is the negative log of this number. We simply substitute the negative log of 7.04 times 10 to the minus 7. So here we're going to type in 7.04 times 10 to the minus 7. Going to hit our log button. We get a negative number. Again, we change the sign. We're at 6.15. The two buttons that are really important to you, log and 10 to the x. The equations that you want to know, 10 to the minus pH, and this guy, by definition, pH, negative log, hydronium. All right, another set. If our hydronium was 10 to the minus 4 molar, what's the pH? It's 4. Take the log of 10 to the minus 4, change the sign. 5 times 10 to the minus 4. Type it in, hit log, change the sign. You should get 3.3. 1.37 times 10 to the minus 8. Type it in, hit log, change the sign. 7 times 10 to the minus 7 molar. Actually, on an exam once, I put this on there, that number, and I simply asked the question, again, this was something that everybody was supposed to get right. Is this solution acidic or basic? Well, you'd be surprised out of 500 people, how many people said, this is neutral. Look at all the sevens there. Well, it's not neutral. You type it in, hit log, change the sign, the pH is 6.1. It's acidic. It's more than 7. And finally, 4.61 times 10 to the minus 5. Type it in, hit log, change the sign. I can't see it. Oops. But nonetheless, we know what's under there. Oh, there it is. 4.33. Any questions? That's pH calculations, guys. We have 2 tutorials that do pH calculations. What's the pH if hydroxide is 6 times 10 to the minus 11? Step 1. We know hydroxide times hydronium is always 10 to the minus 14. Hydroxide times hydronium is always 10 to the minus 14. And we also know that pH plus pOH is always 14. So, 10 to the minus 14 divided by hydroxide is hydronium. Take hydronium, take its log, we get pH. Substitute. This is what we were given for hydroxide. That's our constant. Hydronium is 1.6 times 10 to the minus 4. Type it in, hit log, change the sign, 3.79. Let's do it again. If hydronium is 2.8 times 10 to the minus 3, what's pOH? Well, pOH is the negative log of hydroxide, right? So we'll do the same thing. We know this equation, and we know this equation. Going to take our 10 to the minus 14 constant, divide it by hydronium to get hydroxide. Once we know hydroxide, simply take its log, change the sign, and we get pOH. Substitute. This is what you get for hydroxide, simple math. Take its log, change the sign. Our pOH is 11.5. That's pH 1. pH 2 is even neater. Here you get a table with 4 slots. Only one will have a number in it. What you have to do is type in the others. Okay. We're given a pH here. How do we get hydronium? 10 to the minus pH is hydronium. First of all, we can do pOH right away. 14 minus 10.8, 3.17. If we know the pH, 10 to the minus pH is hydronium, 10 to the minus pH, 1.48 times 10 to the minus 11. Again, hydroxide, we know a pOH value, simply 10 to the minus 3.17, and we've done it. Now, of course, every time you hit new problem, you get a different array. Let's do one more. Here we are given hydronium. We need hydroxide, pH, and pOH. Hydroxide is going to be 10 to the minus 14 divided by the hydronium. Here's our math. 8 times 10 to the minus 12. Our pH is minus log hydronium. Simply type it in, hit log, change the sign. And pOH, we could take our OH value that we have here, simply take its negative log, and we're 11.09. Now, sadly, Blackboard won't let me do this. So I had to come up with a different type of problem. So make sure you understand it by practicing with this guy. Then, when you go to Blackboard to get your points, the following measurements refer to the same solution, but one is wrong. Which one is wrong? And type in the correct answer. Okay, simplest way to do this. We're given a pH and a pOH, right? We know that they must always equal 14. First question is, do they add up to 14? Well, no, they don't. 8 plus 8 is 17. Okay, so either this is wrong or this is wrong. Let's take our pH. Do 10 to the minus pH. That will give us hydronium. So 10 to the minus pH, log hydronium is this, is 8.15. So that works. This one's right, that one's right. We have hydroxide here. This cannot be right. Minus log hydroxide, 5.85. So this guy must be somewhere here. What are we looking for? pOH. 5.85. Again, take the log of that. So, Blackboard just wouldn't let me do it the other way. So we have to live with this one. It's a little confusing, but you'll get used to it. Now, I almost always have an extra credit question on exam 2 that's based on this sort of stuff. It looked like this. We have cheap red wine. Our pH is 2.85. Trust me, that's red wine vinegar. You don't want to drink that. Okay. Calculate the concentration of hydronium, hydroxide, and pOH for your 5 points extra credit. Our first equation, hydronium, is going to be 10 to the minus pH. We know pH. We substitute 10 to the minus 2.85, hit equal on your calculator, we're 1.4 times 10 to the 30. That should be minus 3. I apologize. All right, so I get partial credit. That's hydronium. For hydroxide, we can do it this way simply. We know pH, we know the number 14. We simply subtract them. Our pOH is 11.15. Finally, to get the hydroxide ion concentration, we could simply take 10 to the minus POH, substitute 10 to the minus 11, that is hydroxide ion concentration. Just like the tutorial, except different. All right, this ends the chapter. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tutorials so far. Any questions? Don't get up. I don't want anybody to fall down. We know that we have to have all of these guys done before exam 2, right? Just like happened on exam 1. And there are some of you that did not get them all done, right? I'm sorry. Just to show that I'm human underneath all this, after we complete chapter 9, that weekend, I call Amnesty Weekend. On Friday, Saturday, and Sunday until midnight on Sunday, Tutorial 1 and Quiz 1 will both open up online. You have 3 days, 2.5 days to get these done. Then they disappear forever, I promise. Amnesty Weekend, don't miss it. Here's our tutorials, do them. And have a nice day.